Alright, so today we're going to talk about heating and cooling curves. So a heating curve is when we heat a substance and we see it change from solid to liquid to gas. And so on the x-axis here, you'll either have time or energy that's been added, okay? And then on the y-axis, you will have temperature. And temperature here is measured in degrees Celsius. Of course, time can be measured in seconds or minutes, depending. And then energy will be measured in joules or kilojoules. So if we think about water, right, as we go through changes of water, we know that if this is 0, right, the important parts of water are 0 degrees and 100 degrees, right? And so as we increase the temperature of a substance, when we hit 0 of water, right, when we hit 0, right, it will begin to melt. And we see this plateau during that change. And then when we increase the temperature some more, and when we hit 100, then it will vaporize. Once it has vaporized, we can continue to heat it, and we just change the temperature of the gas. So down here in the bottom section, we have a solid, and then we change it from solid to liquid. We melt it, right? And then here we have liquid, and we change the temperature of the liquid. Once we get to 100, now that liquid becomes gas, right? And we vaporize. And then we can continue to increase the gas. So like in the last unit, we talked about phase diagrams, and we could see the pressure and temperature changes, right? How that affected phase changes. This is just the amount of energy that we're putting into it, or just the amount of time that we allow it to heat up. Some things will go through these just at room temperature over time. Alright, so if we look at a cooling curve, you might expect that it will look the opposite, right? So again, a cooling curve would start, right, with your substance as a gas. Again, we have our temperature in degrees Celsius, and here we would have time or energy. And so for the cooling curve, we would start at a higher temperature, and it would decrease in temperature, right, until it reached a point where it would change from gas to liquid, and it would plateau, and then it would decrease in temperature some more until such time that it would melt. It would freeze, and then we would decrease temperature some more until it would just decrease the temperature of the solid. So again, in this case, this would be gas. This would be our gas changing to liquid, which we call condensing. Right? And then here we would just have our liquid, and then we would have liquid to solid, which we call freezing. And then here we just have our solid. So again, at the phase change, we notice that the temperature does not change, right? So temperature does not change during a phase change. The changes that we do have happening, though, are the molecules getting closer together or further apart. And so there's two types of energy. One is kinetic energy, and that is energy of motion. Right, this is energy of motion. And then potential energy, which is really energy of position, or how close the molecules are to each other. So one is of motion and one is of position or closeness of the molecules. Okay? So on our cooling curve and heating curve here, we have when the temperature changes, if we recall the definition of temperature, right, is the average kinetic energy. And so when our temperature is changing, we have a change in kinetic energy. And I use a little delta sign to represent change. When we're melting, remember the molecules are coming apart from each other, right? And so here we're going to have a change in potential energy because the position is changing. And here our liquid, again, we're increasing the temperature, so we have a change in kinetic energy. Again, we're vaporizing as molecules are moving further apart, and so that's going to be a change in position or potential energy. And then again, we have a change in temperature, so we have a change in kinetic energy. Okay, and of course, since energy here is increasing, right, we're increasing energy. All of these would be, these changes would be positive. Now, on a cooling curve, right, we are decreasing in energy. Okay? In other words, energy is being released, and so all the changes would be negative. So here our molecules, they're changing temperature, they're slowing down, right? So their change in kinetic energy would be a negative value. And then here they're condensing, they're getting closer together. So again, we have a change in potential energy because their position is changing. And then the temperature is changing here, so there'll be a change in kinetic energy. Freezing, they're getting closer together, okay, so then that's change in potential energy. And then finally, again, a change in temperature, so that's a change in kinetic. So anytime we have a change in temperature, we have a change in kinetic energy. Anytime we don't have a change in temperature, we're changing the position of the molecules. And so we're changing potential energy. You do need to be able to label these items on the heating and cooling curve. Okay, these items here. We've talked about solid, liquid, gas, and the changes in potential and kinetic energy. Then endothermic and exothermic. Remember, exothermic means heat is being released, right? And so cooling, this is where we're having our heat is being released. So this is exothermic, right? And if we're increasing energy, we're adding energy in, and so this is endothermic. Okay, so heating curves are endothermic, cooling curves are exothermic. All right, so again, temperature, right? We learned this in the last unit, is the measure of average kinetic energy, right? Absolute zero is 0 Kelvin, right? That's where no motion, there's no motion of particles at all, okay? And then heat, right, is a type of energy, okay? And this type of energy can be transferred, okay? And we'll talk about that in this unit. So first, laws of thermodynamics with law of conservation of energy. Law of conservation of energy tells us energy cannot be created or destroyed. Okay? We cannot create or destroy energy. We can transfer it. Okay, we can transfer it. And you know this, if you touch something that is hot, right, like a hot pot, it transfers to your fingers and it can burn you, right? Good. Okay. We can calculate the energy during a phase change. To calculate the energy during a phase change, we need to know some constant values. Heat of vaporization, again, this is in your reference packet. Okay, heat of vaporization is 2260 joules per gram. Heat of fusion is 334 joules per gram. And again, these are in your reference packet. Also, these equations are in your reference packet on your formula page. Okay. Q represents the amount of heat, and it's measured in joules. M, of course, is mass, and we measure that in grams. Heat of vaporization, we already said, 2260 joules per gram, and heat of fusion is 334 joules per gram. If we get a positive Q, that means it's endothermic. If we get a negative Q, that means it is exothermic. Alright, so let's calculate the amount of heat required to melt 50 grams of water. Alright, so if I have 50 grams of water, Q will be equal to the mass times the heat of fusion. We use heat of fusion for melting. Okay. So the mass times heat of fusion. So Q would be equal to the mass, which is 50, times the heat of fusion, which is 334 joules per gram. And so our grams cancel, and we multiply, and we get our answer. And we get 16,700 joules. Right, we started off with 3 significant figures, and so we can keep 3 significant figures in our answer. Again, our value came out positive, so that makes this endothermic, which we already know that melting requires us to add heat, so that's endothermic. Alright, now we want to calculate the mass of water that can be vaporized. As we're vaporizing, we're going to use heat of vaporization. Right? And so if this time we added 2,500 joules of energy, we want to know what is the mass. Again, our formula is the same, we're just going to use a different constant, heat of vaporization. So here we know joules, right, is our amount of heat. So that's what we put in for Q, that's 2,500, is equal to our mass, which we're looking for, times our heat of vaporization, which was 2260 joules per gram. So then to solve this, we'll divide by 2260. And we'll get that our mass is I can't type it in my calculator today. Is 1.1 grams. Right, so I started out here with 2 significant figures, so I need 2 significant figures in my answer. Right? Alright, so again, these are our values, heat of vaporization, heat of fusion. Of course, these are only for water. We, in this class, will use only water, because that's the one they give us in our reference packet. But if we were given others, they would have different values for different substances. And that concludes the video for today.